Okay, so yeah, I will tell you a few words about the usage we do of Spack and other tools in this in the development and distribution of this PDI library, and some lessons we learned, some things we might not be doing the right way, some things where we haven't found a solution, and yeah, get your feedback maybe about them. So the PDI library, it's a project that is now 10 years old. It's a library for data handling for HPC applications. So basically, you instrument your application with a declarative API, and then in a separate file, you can choose what to do with the data in a declarative way. So we have a lot of plugins. The thing is, each of those plugins, okay, you might see the list maybe if the screen doesn't flicker too much. Yeah. Each of these plugins have dependencies, different dependencies for each of them, and the core library also has some dependencies. So the question we have is how to enable our users to use this library on supercomputers. And first, before we move to that question, let me say a few words about the way the supercomputers our users use in Europe work. So we have first a base system layer that is installed by the system administrators, the system team. They use some RPM-based installation usually. And on top of that, we have a support team that works in the supercomputing center that will install some shared libraries, even some applications that a lot of users rely on. They were used to rely on configure and CMake. Now, hurrah, they moved to Spack, most of them. We see some easy build, some gigs, some other tools. But this team is installing most, or at least a lot of shared library between the users. And here we have an interface that works quite well. Spack knows how to use external, so it can rely on the MPI that was installed on the layer below. But on top of that, we have the users. The users, they might be the application developers, the application users. They come to the machine. They can only install in their home directory, and they're supposed to install their application and maybe a few libraries that were not installed by the support team. And for them, the only interface they have is module. So module is nice, but it's difficult to use a package manager on top of that. There are solutions that work. When the support team installs stuff with Spack, you can change Spack. That's great. But if that's not the interface that the support team offers you, then they do a garbage collect and it breaks everything. Or maybe they don't use Spack. They use a different package manager. So yeah, right now we're kind of in a bad situation here. So we are still using module load and then configure or CMake, make install. And the thing is, those users, they have no internet access maybe. They cannot download anything. Oh, by the way, you're on a file system where inodes are expensive, so please don't use too many of them. So yeah, it's kind of difficult to install stuff here. So when we come back to our question, that was how to enable users to leverage our library on supercomputers, the actual questions become the deployment of a library on a supercomputer. There are two options. Either we get support on board and they install the library for all users, or the support team says, no, this library is too application specific, so please install it yourself, and then we have to offer a solution that works for the final user to install the library on the supercomputer. So yeah, how do you package and deploy a library in a way that works for supercomputer users? The strategy we have, the library, it's a single repo, but in the repo we have multiple directories that are independent CMake projects each. So each of them does a CMake find package, add library, install, and the plugins, for example, they depend on the core library, but they do a find package for the core library. And then the question is, so we have multiple projects, how do we do the meta build for all of these projects? We have created multiple options over time. The first one we did is to create a CMake super build. So you have a CMake list at the root of the meta project, and when you configure with CMake, it will look at the dependencies between the project. It will maybe even, and that's optional, but detect the already installed dependencies. We have vendored some of the dependencies, so it can also install them, and it will configure everything that needs to be installed. Then when you do the build, the make step, for each package, it will build the package, and it will install it in a staging directory. And then for the next package, it will use what's already installed in this staging directory. And installation is just copying the staging directory to the final installation path. Well, we have to hope that everything is relocatable. We don't do anything about that. Kind of works. We tried moving to something a bit more recent, like add subdirectory and fetch content that works well for dependencies that support that. But if you have a non-CMake dependency, if you have a dependency that doesn't support add directory in their CMake, it just doesn't work. So for now, we cannot do it. So what's good about that? The good is, well, we can distribute a single tar file, and everything is auto-detected. The user, they just do CMake, make install, as they're used to, and it works sometimes. The thing is, the tarball is huge. It contains our source code, but it also contains the source code for each of our dependencies. And if you start imagining everyone doing that, everyone install their own dependencies and package them, and then each dependency we package already contains it, it doesn't work. And the thing is, as much as I love CMake, the CMake language is not something I would recommend to write a package manager. Yeah, the thing is, what we have done, it's extremely sensitive to a lot of things. It's always broken. And we realized at some point, we manage dependencies. We are writing a package manager in CMake. That's not the right tool. There are package managers that exist. And so we looked back then what were the normal package manager everyone were using, Debian, RPM, so we did that. We created our own Python script to build the package in Docker with 0 additional dependency added to be sure that we don't rely on something we don't claim to rely on. We have a repository with the source packages for Debian, Fedora, Ubuntu, for each version that we claim to support. And we build that. We have a nightly build for the top, the main branch of the library, and we have a release branch that we build weekly with the latest release of the library. We rebuild weekly because some of the distributions we target are rolling release. So while our package don't need rebuilding technically more than when we release, some of their dependencies might be broken in between, and we don't have something automated to handle that yet. Then it's deployed to a binary repository. So that's nice. Using an actual package manager to do package management, that's great. Our users, when they can use that, for them it's easy, it's fast. They just add the repo and then apt-get install. Works. So for many of our users, that's the way they use the first time the library. The thing is, can only support a limited combination of options. What is the MPI provided by the distribution? What architecture do they build for? It's a lot of maintenance. The format for these packages are not always the easiest to use. And all distributions, they might lack some dependencies we require. But yeah, that's not too bad. The thing is, to do that, you need to be root. So it doesn't solve our problem on supercomputers at all. Luckily, and you see where I'm going, there is a package manager that basically does all of that in the right way. So we did some Spack recipes. We have an external repository for recipes that is not a full fork of Spack. We support that in order to support all Spack versions. So we have recipes that work with Spack up to 0.18. And we also upstreamed recently the recipes to the main repo. There are a few things we do in what you might call a strange way. I hope our recipes don't get kicked when I show that in the next slide, but we'll see. And for each new release, we make new recipes. And we test that in Docker with some combinatory. We test the oldest version of Spack we claim to support, the latest, the developed version. We test multiple compiler version. We test multiple MPI version, and we test the oldest and latest version of the dependencies also. So our recipes, first, in our separate repo, we want to support old Spack and new Spack at the same time. So we have a few conditionals. We import things from different places depending on which Spack version. We test what's the version of Spack to use the right syntax for some things that changed in between version, the maintainer, the license call that is not supported in the old version. The language dependency, that's new, so if we add that to the old Spack version, that doesn't work, so we also hide that behind a check. But that's for our own separate repository version. Then there's a second thing we do is we factorize between our recipes. So the PDI core recipe specifies the list of versions, but then all our plugins have the exact same set of versions. So in the plugins, we import the core package, and we reuse the versions from the core package in the plugin. We might be using some private API here. I'm not clearly sure about that. I don't know how long it will work, but for now it does. We also have strict same version dependency between the plugins and the core, which means that for our dependency, we used to list if the version is this, then I depend on the core library with the exact same version, et cetera, et cetera. We've moved that to a loop where basically we iterate on all the version and inject those dependencies. I don't know if there's something better to do here. And finally, the package, the tar is the same. It's just subdirectories in a single tarball. So we reuse the function from the core library to get the URL in all the plugins. So in the end, we have something that works great. That works great to install on supercomputers by the support team. It supports variants, it supports constraints on the dependencies, it supports multiple computers. Being sure that the range of dependencies we claim to support is correct is something very difficult to test. There is some combinatorial explosion here, and I don't think anyone does any reasonable or realistic testing of that. And the problem is we haven't solved the issue for end users that want to install on supercomputers. The using Spack for them means the inode limit might explode in their home directory. It's possible, but it's not as easy to use Spack without an internet connection. And reusing the system packages is a problem. Some teams use, as I was saying, easy build. Some places you cannot chain the Spack. So we don't really have a perfect solution for this use case yet. So as the takeaway, we have supported 3 options for packaging. There is no one-size-fits-all solution, and we don't have a solution for our end users that is perfect yet. I hear people tell me, the solution, that's containers. That's the way you distribute stuff nowadays. Stuff, but libraries? No, you don't distribute a library as a container image. So what I would love, and maybe we can talk about that, is to have Spack as a service. So the support team, can they install a Spack, and me as a user, I just do Spack install, not in my home directory, but that's a request for the system Spack to install something. That's what I would love to see. And beyond the installation itself, the big problem we have is the testing of all that. Do we use some features of libraries, versions that are more recent than what we claim to support? Some libraries, they have variants, the header-only version or the compiled version, they don't work exactly the same. Some libraries change behavior in the latest variant version of the library. We have multiple MPI implementations that don't behave exactly the same. So the thing is, we really need testing, and for that, we leverage what we've done. We build, using the CMake super build, in a set of Docker images that combine multiple versions. So we have Debian, we have Ubuntu images, the oldest LTS that we still support, and the latest release, OpenMPI plus mpich, and either including the vendored libraries, so we don't rely on vendored libraries and use the system libraries, or excluding them to test our super build and see if we actually support installing the vendored libraries. Same with Spack, oldest versus latest. All the compiler, all the MPI implementation, vendored or not vendored. And what we see is that many bugs happen in 1 or 2 specific cases of this matrix. So that's really useful. The way we build our image, well, for Debian and Ubuntu, it's pretty simple. For Docker, for Spack, it's a bit more complex. We want to create an environment where we can test things. And in this environment, we want our compiler and libraries. So we install the compiler twice. We install it once, and then we compile it with itself to be able to put it in an environment where everything is compiled with the same compiler. That might have improved with the latest version. But in the end, we end up compiling the compiler maybe 4 times, because internally, the compilation of the compiler itself has this bootstrapping process. So it's a bit long. The result is a bit complex if we look at all the repositories we have. But this is really great to be able to do this testing. Unfortunately, we wanted to test the specific oldest library we claim to support. And that's too much work. We end up always installing something with Spack that is not the default version, that is thus not tested, and the package are, sorry to say, all broken in that respect. If you start installing something that is not in the default version, that doesn't work. So we choose to instead move to 0.18. I see Todd disagreeing, but OK, we can talk about that. And for us, Spack is really moving in the great direction with language as a dependency. It will improve our situation a lot, even if for now it broke our workaround for when it was not like that. But yeah, in the long run, it's great. The stable package API is also something we really want. So that's great. Thank you for that. And I will leave you with this takeaway message. This is really what I would like to have to be able to work and distribute our library on supercomputers. Thank you.
We have probably time for just one question. Not you. Okay.
So how would you handle a build failing under Spack as a service?
Sorry, can you say again?
How would you handle a build failing under Spack as a service? So let's say it fails, you have to fix it. How do you do that?
The thing is, what I would like is just to have Spack install that gives me the same message I get when I do Spack install in my own Spack. Just it's done in a shared file system so that if 10 different users do the same Spack install, they don't end up installed 10 times. I think in CSCS they have something that goes that way. That's something I would like. Yeah. How to handle failure? You get a message, you send a message to the admin if the packages are broken.
All right. Thank you.